Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. Today we're going to look at an interesting concept in mechanics, and this basically is going to be dealing with the concept of potential energy. Now this is going to be borrowing from the previous discussions whereby we have come across particularly the three terms which have used in this case for mechanics, potential and energy. And of course we're going to look at this specific concept through an analysis of the illustration which I've given on my left side of the board. And this is going to be emphasizing particularly on the concept of what we refer to as a gravitational potential energy, which is going to be one of the main topics of this specific kind of potential energy that we're going to look at. Now, in this particular case, I'd like to request our members to kindly subscribe, engage us in the comment section, and also ring that notification bell to be getting updates on various uploads we do in mathematics and sciences. Now, in this case, I'm going to remind us of this specific concept which we have come across in one way or another in most of our discussions. And this is basically the concept of mechanics. Now, we had defined the mechanics from our previous discussion as a branch of physical science, which mainly deals with the concept of motion of bodies. And this, of course, is going also to entail the concept of energies which are going to be associated with these particular bodies, and of course the forces which are going to be involved in this specific aspect of motion. And this basically are going to be summing up this specific aspect of the concept of mechanics. Now, in that particular case, we're going to look at this aspect of energy, and this will have a relationship with various, of course, forces which are going to be involved. And this particularly is going to be concerning with the energy, which is going to be the energy at rest, and some of the effects of forces on these specific objects, which are basically stationary or at rest. Now, therefore, we can, in a summary form, define mechanics as a branch of science that deals with the energies and forces and their effects on bodies. And some of our texts which we are going to come across, it can be defined as a branch of physical science that is concerned with motion of bodies under the action of forces. And that's going to be, in a way, giving us a clue on what basically this aspect of mechanics is. Now, concerning the concept of potential energy, and therefore, now that we have looked at the concept of mechanics, now potential energy basically is the energy that is possessed by bodies that are stationary or bodies which are at rest. So this is basically the energy possessed by bodies which have said which are at rest, or sometimes we can regard these bodies as stationary in this specific case. So we're going to look at the forces which are going to be involved in this particular case, and how we can describe some of the aspects of energies which are going to be, of course, be possessed by these specific bodies which are at rest. Now we're going to consider a system that is going to be having particularly two or more bodies. And in this case, have in mind of the previous discussion which we have done, of course, on various forces, especially on the Coulomb's law, whereby we see that we can have a relationship between bodies which are, of course, adjacent to one another. And this is going to form a system of two bodies, which we had first discussed in terms of charges, and which were, of course, particles possessing charge given as such. And we said that there is going to be some forces of either repulsion or attraction depending on the nature of the charges which are being possessed by these two bodies. So in case we give this one as A and B, we're going to see that there's going to be repulsive forces which are going to be, of course, realized in this particular case, whereby the force being acted upon a B is going to be a force due to A. And of course, we're going to see that this is going to be a repulsive force, and the force acted on A is going to be a force, of course, due to B. And this is also going to be a repulsive forces. Now, we're going to expect the opposite to be true if we're going to have a negative, of course, charge in this particular case, which is going to obey the laws of attraction. Now, in this case, there's going to be some factors which are going to affect the nature or the magnitude of these particular forces. One of them being the distance of separation, which I've particularly given in terms of d in this particular case. Now we're going to see that due to this specific nature of the interaction of the bodies, we came up with the Coulomb's law, which basically tried to look at the amount of charges and the distance of separation, of course, and the vector, unity vector in that of this specific force in that specific direction. And we had said that these are some of the factors which are going to affect the magnitude of this particular force, which entailed the charges possessed by these particular bodies, and of course the distance of separation. And in this case, we're also going to see that especially the concept of distance is going to heavily affect the amount of potential energy, depending on the nature of this specific type of energy which we are going to see. Now, basically, then, therefore, we are going to expect that this aspect of separation distance is going to be one of the arrangement setups which are going to affect the nature of the forces between this one. And also the charges are also going to be one of the factors being considered in this specific case. Now, therefore, altering the arrangement of the system is going to change also the nature of the potential energy, which we are going to look at shortly. And of course, we shall do this one in looking at the two types which are mentioned, perhaps in trying to list them, and then we narrow ourselves down to the gravitational potential energy. Now, we have two forms of potential energy. Now, the first one is gravitational potential energy, and then we're going to have another one referred to as elastic potential energy. Now, these are going to be the two forms of potential energy which we are going to heavily rely on. And of course, we are going to be looking at each of them in an exclusive way, whereby I'm going to start with the elastic potential energy. Now, if we consider an object that is falling towards the surface of the Earth, so let's consider this as an object, and then we're going to have the surface of the Earth being given as such. So we're going to expect some forces to act on this specific, of course, falling object, and this is going to be regarded as the gravitational force. Now we're going to give this gravitational force in terms of G. So in my discussion as we are going to go ahead, this specific initial for G is going to refer to as, of course, basically we're going to give this gravitational force, sorry for that, gravitational force in terms of F subscript G. And this is going to be the initial for this specific force which I'm going to be using in our discussion. Now in this case, we're going to see that particularly this particular force is going to be realized, and it's going to have a specific magnitude and direction, and it's going to be directed towards the surface of the Earth, as we have been shown using that specific arrow. Now this force is going to be of course directed in the direction of motion of that specific object, and of course we're going to see that the gravitational force is going to perform some work on this object, and therefore that's going to lead to increase in the kinetic energy of this specific of course object. Now we're going to consider the system which I've given on my right side of the board. So perhaps I can give this one as a figure 1 just for easier reference. So therefore we're going to consider figure 1 for our illustration purposes. Now in this case, in figure 1, I've got this specific object which I've given in terms of W. Now W is going to be the weight of this particular object, which has been given in terms of mg, which is a mass times the gravitational constant, which I've given in terms of g. Now the distance of separation between the height of this object and the ground level, so we're going to consider this one as the ground level given as such, can be given in terms of yi. And of course, we're going to see that this object is going to fall to a distance whereby I've demarcated this one in terms of, let's give this one as W prime. So in this case, this is just the same object, but I'm just giving this one for the sake of a reference. So we're going to see that it's going to move a distance, a particular distance, to be at the position of W prime. And therefore, the distance covered is going to be the difference between Y initial and Y final, which is the difference between this specific second position and the ground. And therefore, this distance is going to be regarded as a D. And we can use this specific illustration in order for us to do an analysis of this specific object falling through a particular height, which we have given in terms of Y. And therefore, the product of the forces and the mass, which we're going to see, is going to be giving us what we refer to as the potential energy, or the product of the force which we have regarded as gravitational force, and the height which we are given in terms of Y, is going to be defining our potential energy. Now in this case, if we are going to use this specific figure, then therefore, as I've said, W is going to be the weight, and then y is going to be the height in this specific case. And d, of course, is the difference in distance which has been given as y initial minus y final given as such. So we're going to consider also the position. Now, if we assume that the air resistance of this specific illustration is going to be negligible, then we can find the, of course, work that is done on this specific object as it falls to the ground. And we're all going to consider this gravitational force as it's the only one that is going to act on it, as we have neglected air resistance. Then therefore we can evaluate the work done by gravitational force on this specific object. Now, from our last discussion on the concept of work, we had said that work can be defined as the product of the force times the distance which this, or the force acting on an object times the distance through which this object has been displaced. And this, of course, as we have said, we can give, perhaps I can just give this one as such. So we're going to give this force in terms of F, and this is, of course, equivalent to, as we've said, the mass times the gravitational, of course, constant which we have given as such, or the acceleration due to the force of gravity is given as this. So this is going to be a derivation of Newton's second law of motion. And of course, this is going to be given. Now, therefore, we can define work, which is a W in terms of a force times the distance. And these are going to be vector quantities. So we're going to have this one work as a force, which is mg times the distance, of course, which is going to be the distance of separation given as such. So in doing our substitution from this specific case, we had the value of d given in terms of y initial minus y final. Therefore, implying that work is the same as mg times y initial minus y final given as such. And we're going to see that as we considered the only force, the gravitational force, as the only one that is going to be acting on this specific object in this particular case, we're going to see that if we consider the dot product of this specific, of course, direction which we have given in terms of motion of this object. Now, from the three Cartesian coordinate system, we had said that we can give these unity vectors in terms of, so this is going to be I and j. So therefore, we are going to consider the fall in the y direction, which is going to be j. Now, from this particular case, if we're going to do an analysis of this specific, of course, equation, we're going to see that the components of the j and j, which is the point of motion of this, or the direction of force of this specific object, is going to be 1, which is a unity. Therefore, we are going to see that this can be given in terms of, so the work can be given in terms of mg, which is acting in the y direction minus mg. And of course, so there's a difference between yi and y final. As we're going to see this, and these ones are going to be constant values. Now, therefore, we can also consider the case of a body, perhaps, which is not going to be moving only in the vertical direction, but is taking a displacement both in the x and the y direction as it falls to the ground. Now, in this case, we're also going to see that the analysis of this specific kind of force is going to result in this specific equation, due to the fact that if we consider the displacement in the x direction, that is going to be an I multiplied by a j. Perhaps I can just try to give this one in an elaborate form. So we're going to consider this one moving in a single direction over the y-axis. This is going to give us the formula for the work done on that specific object. Now we're going to consider perhaps a body that's going to undergo both horizontal and vertical displacement. And therefore the difference in distance can be given in terms of, let me show that one. So suppose we consider that specific body which I've given using this symbol illustration. So we're going to see that the body is going to be moving perhaps as it falls in the x and y direction. So it is being displaced downwards as well as the horizontal direction. And therefore we are going to expect our d to be the difference both in the x and y direction. So therefore we are going to have this one given in terms of x displacement for x final minus x initial. And then we are going to have a plus the displacement in y is y final minus y initial given as such. And if we consider through this, we had said that this basically is going to be given in terms of the I and the j according to the coordinate system which I've mentioned. or the two displacements for the Cartesian coordinate system for x and y given as such. And therefore, if we're going to multiply mg, which is our force, definitely we have said that this is going to be directed in the I direction, and therefore times the distance, this is going to be giving us, of course, this one. Okay, let me give it in this specific format so that we can just do a follow-up. So I'm going to give this one in terms of a combined equation, whereby we're going to have this one given in terms of the work done is equivalent to mg times d. Then in this case, we are going to do a substitution for d, and I've mentioned that this specific, of course, g is going to be directed in the y direction. So therefore, I'm going to give it in terms of basically j direction, which is a downward motion, and therefore I'm going to give it in terms of that specific notation. So if we consider this one, we said that we're going to see that the work done is going to be given in this negative, the work done is going to be equal to the negative change in the system's gravitational potential, and therefore that's going to be a negative value given as such. So we're going to consider this a specific aspect of d by doing a substitution of this one which we have given in our equation above. So I'm going to do just a substitution for that, and for the displacement of x initial minus x final, and then we are going to have, so this is going to be in the I direction as I've illustrated, so plus the displacement in the y direction, which is going to be y final basically, minus the y initial given as such. And as we're going to see, this y displacement is going to be in the j direction given as such. So if we consider these vector quantities or the unit quantities for those two specific vectors, a multiplication between this j and I, as we said that basically from vectors I times I is equivalent to j times j, which is equivalent to, of course, k times k, which is equivalent to 1. So this is the x, y, and z. So from vectors, we can borrow that specific concept and see that the multiplication between mgj and this aspect of I is going to be 0. Therefore, we are going to consider mgj and the displacement in y, which is a j component given as such. And that still is going to give us the values of the work done given in terms of the negative value, as we have said, mg. And then we are going to have y final minus y initial given as such. And the j and the j components, which are going to be giving us a multiplication of 1, of course, are going to cancel out. And still we're going to have this specific value giving us the work done, or the work done, which is equal to the negative change in the system's gravitational potential energy. Now that's going to sum up for us the work done, especially in terms of the change in potential energy, or the gravitational potential energy. And in our subsequent videos, we're going to look at evaluation examples, which are going to assist us in trying to see basically how we can do an application of this specific, of course, formula which I've given, or the formula which I've given in our question set. So that is it for now, guys. Kindly check our description boxes for various links of other videos. Subscribe and engage us in the comment section for more. So that is it for now, guys. Bye. God bless you. Catch us in our next video.